discussing problem 9-3 in the E&M section. Alright, so I've taken the liberty of drawing out this circuit, and it's given all the knowns. Alright, so we're ready to go. Determine the energy stored in the capacitor when it's fully charged. This is a very simple problem. All you need to do is look at the equation sheet and recognize that the potential or total energy stored in the capacitor is 1/2 CV squared. There are two different ones, but this one would work well given the knowns. And so now you just plug everything in. 1/2 6 microfarads times 20V squared, and your total answer is 1200 microjoules. It's important to put the units. You never know whether they're going to count it or not, so just put it just in case. And that's part A. Simple enough. Alright, part B. So now they're saying that the distance between the capacitor plates are suddenly increased 4 times its original value. And now we have to determine the work that's done in increasing the spacing. Alright, so first of all, let's consider the fact that total work is also equal to the change in potential energy. So that's our final goal, to figure out the change in potential energy between the final capacitor and the initial capacitor. So how do we get there? So we recognize that the circuit is a series, which means that the Q is constant. And we can manipulate this with the equation C is equal to Q over B. So Q is equal to CB. So if Q is constant between the capacitors, then we can write that CV is equal to C prime V prime. This is the original capacitor, this is the capacitor 4 times distance, whatever, yeah. Okay, now that we have to determine, since there are 4 different terms, we need to just get it down to the 2 original terms given to us and figure out how to convey these 2 in those things, if that makes any sense. Alright, so first, the relationship between C prime and C. So the equation for a capacitor is like so. It's on the equation sheet. So if we increase the distance, which is down here, 4 times, that means that your capacitor value is decreased 4 times its original value. That's important. You don't want to confuse it for 4C. Nope. It is C over 4. Alright. So now that we've got that established, we can write that C prime is actually equal to C over 4. And now we plug that in over here. And we get that V prime is actually equal to 4 times the initial voltage value. So we got all that in. Now we can go to this equation over here. Delta U. So UF minus UI. So the equation for U for a capacitor is 1/2 CV squared, as we saw in the previous part. So for this, we got 1/2 C prime V prime squared minus CV squared. And we can plug in all that we found. So C prime was C over 4. And then we got V prime, which is 16V squared from over here. Plug that into V prime here. And then CV squared, we got those. We don't need to change anything about that. So these go away. We get work is equal to 1/2 4CV squared minus CV squared, which is equal to 1/2 3CV squared. And now all we need to do is just plug in the values, and we've got our C value, 6 microfarads, we've got our V value, which is 20 volts. So all plugged in, we get work is equal to 3600 microjoules. Just to reiterate, that's 6 microfarads, V is equal to 20. We are good on this problem. So part B, work is equal to 3600 microjoules. Cool. Okay, next part. Okay, part C. Determine the current immediately after the spacing is increased. Alright, so for this one, we can use Ohm's law provided by the equation sheet. V is equal to IR. In the last part, part B, we established that V prime is equal to 4 times the original V value. So to find the new V prime, we substitute that into here. So 4V is equal to IR. And now so this is the final voltage. So we've got two voltages we need to consider. So that would be 20, the initial voltage, and then the final voltage, which is 4 times 20, is 80. So that's 4 times, after the spacing is increased 4 times original value. Alright, now to find current, it's basically delta V over R. So it's literally just 80 minus 20 over our resistance, which is a whopping 300,000 ohms. And just if we solve for that, we get 2 times 10 to the negative 4th amps. And that's the answer for part C. Pretty simple. You just gotta recognize that you have to find the delta V, find the voltage after the spacing is increased, because that's pretty important. Okay, let's done with that part. Okay, part D, determine total charge that is passed through the battery. Alright, so this is pretty simple. The total charge of a battery, well, C is equal to Q over V, which means that Q is equal to CV. So now let's find the initial charge in this circuit. So we got 6 microfarads times the initial voltage value, which is 20V. And that is 120 microcoulombs. Now for QF, our C value, as established in part 1, our C value is decreased 4 times when the spacing is increased. So we got 6 over 4 microfarads times 20 volts. This is the same because it's the EMF. That doesn't change at all. And then that's just equal to 30 microcoulombs. So now our delta Q, which is very simple, is basically 120 microcoulombs minus 30 microcoulombs, and our final answer is 90 microcoulombs. So that goes for part D. Okay, cool. Now finally, part E. Determine the energy that has been added to the battery. So when they're talking about energy being added to a battery, we know that it's talking about potential energy. And if we look on the equation sheet, one of the equations is like so. The potential energy of the electric field is equal to total charge times the voltage. So in this case, if we're going to put into terms for this problem, total delta E, which is the same thing in this problem, is equal to delta Q, because there's a change of charge, times V, which is just the EMF. Alright, so now we just plug everything in. We got delta Q in the previous part, which was 90 microcoulombs, and we know what the voltage of the battery is. That's just 20V. So our final answer is 1800 microjoules. And that is the end of the problem here. The answers. Hope you had fun.